In this video, we will start to talk about Chapter 5, the concept of mole and writing chemical formulas. The concept of mole is very important in chemistry, and we are going to be using it for the remainder of the semester. So I suggest that you watch the video several times, read the book. I will have supplemental videos on this concept until you fully grasp it and know how to actually work with the conversion factors that we're going to talk about. We will be slowly adding on to the concept of mole as we continue on into the semester, so it is important that you understand it now. Here's sort of an overview. We will talk about counting atoms by weighing, which is similar to molecules, but instead of atoms, you have molecules. We will then move on to percent composition, how to use mass percent to determine the empirical formula, and then coupling empirical formulas and molar masses to determine molecular formula. Now, these are going to be separate videos. Right now, we're going to focus on the first heading here, counting atoms by weighing. When we talk about atoms, we are talking very, very small scale. Atoms are so small so that I cannot talk in terms of one single atom. And especially in the laboratory, it's very unpractical to talk about very small quantities such as atoms. To be able to move from the tiny atoms to macroscopically to weigh a sample in a laboratory, I have to have enough of these atoms together to be able to measure their mass, because the mass of one atom is so small, I can't possibly weigh it on a scale, or even 10 atoms. So I have to have so many atoms together. I mean, a very, very large number of atoms together in order for me to be able to go to a scale in the laboratory and measure 1 gram or 5 grams or whatever the case might be. So even the smallest quantity of atoms of matter contains an enormous number, the smallest quantity of matter contains an enormous number of atoms because the atoms are so small. So instead of counting individual atoms, we use a unit of measurement that is called the mole. Not the animal, but it's a measurement of atoms, short for mole. Now here's an idea we are used to. When I say a dozen, everybody knows that a dozen is equal to 12. A dozen eggs is equal to 12. A dozen roses is equal to 12. A dozen of anything is equal to 12. So the dozen is equivalent to 12 all the time. It doesn't matter what I am measuring. Very similarly, the mole is a term, just like the dozen is the term of measurement, but instead of equaling 12, it equals what we call Avogadro's number, after the guy who discovered it. So the mole is equal to 6.022 times 10 to the 23rd. And these could be atoms, they could be molecules, they could be donuts, they could be whatever. So it doesn't really matter what I'm measuring. The mole is equal to this many individual pieces. Just like the dozen is equal to 12, the mole is equal to 6.022 times 10 to the 23rd. Note that this is a huge number. So it's 6.022 times 10, so it's 23 zeros. That's a very, very large number, but we have to use such a large quantity when we're dealing with little atoms that are so tiny. So we have to pack this many of them to be able to have the mole and to be able to measure it practically in a laboratory setting. So as I said, this is known as the Avogadro's number. Its symbol is big N with a subscript of big A. So Na stands for Avogadro's number. Now the definition of Avogadro's number is the number of carbon atoms that are contained in exactly 12 grams of carbon-12. So if I had carbon-12 isotope and I measured exactly 12 grams of that, I would have 6.022 times 10 to the 23rd carbon-12 atoms. I would have exactly that. This is made for ease for us to actually, so everything else in the periodic table is expressed in terms of the number of carbons, and so everything is relative to this number. A mole of something, so it doesn't matter what the something is 6.022 times 10 to the 23rd of that thing that we're talking about. Practically speaking, we're going to talk about atoms and molecules because they are so small that I need this many of them to make something macroscopic enough, large enough macroscopically that I can measure practically. Now, when we use Avogadro's number to do calculations, we can use the conversion factor and express it in two different ways. So as two fractions, right? 6.022 times 10 to the 23rd atoms or molecules over 1 mole of atoms or molecules. And these could be potassium atoms, sodium atoms, water molecules, carbon dioxide molecules, so whatever I'm talking about, it could be either atoms or molecules. Or we can flip that, 1 mole of atoms or molecules over 6.022 times 10 to the 23rd atoms or molecules. I will use one or the other depending on whether I'm calculating moles, so I start with atoms and I want to end up with moles, or if I start with moles and I want to end up with atoms. If I start with moles, I want moles at the bottom and atoms or molecules at the top. If I start with atoms or molecules, I want moles at the top and atoms or molecules at the bottom. So I would use this particular conversion factor instead of this one. So let's take a look at an example problem. Calcium is the most abundant metal in the human body. A typical human body contains roughly 30 moles of calcium. So let's determine the number of calcium atoms in 30 moles of calcium and the number of moles of calcium that are contained in a sample that has 1.00 times 10 to the 20 calcium atoms. Now I'm going to do A for you, and then I will give you a chance to work on B on your own. Similar to the previous videos, we always start with the amount that we are given in the problem, so 30 moles of calcium. Now we have two different conversion factor forms, so we have either this one or this one. The important part is to determine what am I starting with and what am I asked. I am starting with moles and I'm asked to figure out calcium atoms. So I want moles to cancel because I'm starting with moles and I want to end up with atoms. So I pick out of these two, I pick the one that will have moles at the bottom and atoms at the top, which is this, this one here. I thought I had made a mistake, but it's this one, right? Because I have 1 mole at the bottom, which will cancel with my moles of 30 moles up here. And then at the top, I have atoms or molecules, and I want that at the top. I want to end up with that. So if I write it, so here's my problem. I set it up this way. I have 30 moles of calcium. Always start with the amount you're given, not with the conversion factor. So I have 30 moles of calcium times my conversion factor, which is 6.022 times 10 to the 23rd atoms of calcium per every mole of calcium. So since I have 30 moles, I'll have 30 times that many atoms, right? And my moles are going to cancel, right? Because I have moles at the top and moles at the bottom, so they will cancel. leaving me with atoms. And if you do the calculation correctly, you should get 1.8066 times 10 to the 25th calcium atoms. Or here's a little bit of review on significant figures. These, once again, are conversion factors, so they don't count when we look at how many significant digits my answer should have. Only what my measurement tells me. So I have 30 moles of calcium. Because I have a decimal point here, these trailing zeros are all significant. Therefore, my starting number here has 4 significant digits. And my final answer should have 4 significant digits. My calculator gave me 5. Therefore, I have to cut off. So 1, 2, 3, 4. If I draw a line between these two 6s here, and I will cut off whatever comes after 4 digits. Since then this 6 is larger than 5, I will have to round up and make that a 7. Here's my answer with the correct significant digits, 1.807 times 10 to the 25th calcium atoms. Stop and ask yourselves if this answer makes sense. So if you had used this conversion factor instead and divided by this, you would have a very, very small number. So if you have 1 mole of calcium, you have 6.022 times 10 to the 23rd. If you have 30 moles, that means you will have 30 times as much. So a much larger number of atoms. This is kind of sort of a way to check whether you have done the conversions correctly. So for the second problem, you are given atoms and you are asked to figure out moles. Therefore, your number of moles better be small, a small number, less than 1 or 5 or 10 even, but nothing times 10 to the 20 or to the 25, because that large of number of moles is way too large. So these large numbers are when we're counting individual atoms, not moles. Moles, 1 mole contains 6.022 times 10 to the 23rd. So for the next problem then, obviously you won't be able to use this conversion factor because it will give you a wrong answer. It will give you way too large of an answer for moles. Okay, I will give you some time to work on this, and then we will continue our discussion on the 5.2 section.